My friends, we're going to determine which way a reaction will shift by comparing the reaction quotient Q, sometimes this is seen as K trial, versus the equilibrium constant K. And we're going to do that without using ice tables and by going through some real exam problems that may be coming up on your midterm or final exam. So let's jump into it. So here we are, number one. So for the system, and we have this equilibrium constant, and this is an equilibrium constant because it's a capital K, and C means for concentration, and it's a specific for a specific temperature, and here it's at 70 degrees Celsius. We don't really care about that. And here's our equilibrium reaction right here, and you see these are aqueous, they're solutions. Makes sense because we want a concentration here. And then the question is, initially all concentrations are at 1.50 times 10 to the negative 3 molarity, which is moles over liters. And the question is, which way will the reaction shift? So this is our equilibrium constant, and we need to achieve this number. Right now, I don't know if we have this number. We need to calculate that. So we need to calculate Q, and Q is where the system sits right now, and it tells us if there's too many products or reactants initially. So Q, just like K, the equilibrium constant K, is products over reactants, and it's based on the initial conditions or any at any given time, really, concentrations at any given time. So the products are right here, the iron 3 plus and the water here. So it's Fe3 plus. Now, concentration of this. Now, we don't include the water, even though it's a product. We don't include the water because it's a pure liquid, so we don't include pure liquids or solids, so we'll just ignore that. It's basically 1, so we just don't include it. Over the reactants, so the concentration of FeOH3, and that's supposed to be closed brackets, and the concentration of H plus. Now there's a 3 here, so that means we got to take this to the power of 3, just like this. Okay, so this is products over reactants, and now we'll plug in the concentrations for all of them. So it's 1.50 times 10 to the negative 3 molarity, all divided by, and 1.50 times 10 to the negative 3 molarity. It's supposed to be a 3. And then lastly, 1.50 times 10 to the negative 3 molarity. Okay, and this is cubed to the power of 3. Okay, so we can do some of this in our head, I think, and we can cross these out. So we have 1 over this cubed. I'm going to plug that into our trusty calculator. Okay, so we got 1 divided by 1.5 times 10 to the negative 3 cubed. So that is a huge number. 1, 2, 3, 4, 5, 6, 7, 8. 2.96 times 10 to the 8 equals 2.96 times 10 to the 8. So now this is what we're at now. So we have a lot of product, right? Times 10 to the 8 over reactants. So if we look at Q and we compare it to K, Kc, which is the equilibrium. So Q is where we are now, the ratio of products to reactants where we are now. And that ratio is 2.96 times 10 to the 8. So this is like 2.96 times 10 to the 8. It's like that divided by 1. You could think of it like that, divided by 1. So if we had one reactant, and this is kind of hypothetical, one reactant, we'd have 2.96 times 10 to the 8 products, very loosely speaking. So we have a lot more products than reactants. What is our K at? K is 1.6 times 10 to the 4. So K is 1.6 times 10 to the 4. A lot smaller, right? K is a lot smaller. So Q is greater than K. Q is greater than K. That means the reaction, this number has to go down because we need less products. We need more reactants, we need less products. Right now we have way too many products. So this number needs to go down. So that means in order to get less products, I'm going to go up here to our equilibrium reaction, we need to shift the reaction to the right so that some of these products react and turn into reactants a little bit quicker than the other way around. So this needs to go down. So in order for this to go down, the reaction has to shift left. And I'm going to show you a shortcut in a minute. Reaction shifts left to achieve equilibrium. And we can, a way to kind of a shortcut to memorize this, or you don't really have to memorize, I guess, but see this inequality sign? This is like the alligator here, or like, this is like the Pac-Man Think of it as Pac-Man likes to eat the bigger number. Well, the Pac-Man's facing to the left. And that's the way the reaction shifts. So if you always draw this with Q on the left and your K on the right, whichever the way the Pac-Man is facing, that's the way the reaction shifts. Okay, well, hope you'll get 100% on this stuff. Should be good. The method never changes. Now, this one has to do with gases. So I wanted to give you a gases example, but nothing changes. It's literally the same. So for the system, Kp, and P is just for pressure. Pressures, 1 equals 1.9 times 10 to the 19. Which way will it shift? This is our equilibrium reaction right here. And we have some initial conditions just like this. So if we want to know which way it will shift, we need to know what our Q is. So Q is products over reactants, and that's going to be, now these are all gases, so we're going to include all of them. And these are our pressures in bars. Actually, I'll write it out. I'll write out the equation. If you screw up your numbers, it's always good to write out the equation because your prof will give you, well, hopefully will give you part marks. Let me know if your prof doesn't do that kind of stuff, but hopefully they should. Okay, so and then the reactants are CCl4 squared times O2. Okay, and these numbers go as the exponents here, so we'll just plug this in. This is 150. Now, I'm not going to use and plug in the units, and you might say like tis, Terry, and I'm the biggest person to say always put in your units, but these constants, these equilibrium constants and Q constants, they're actually unitless. So actually, if we go back a minute, I think this is important. See how the molarity, M, these don't totally cancel out, but Q is unitless. And if you want to know, this is more like a second year physical chem thing, where these are supposed to be activities which are unitless. You divide it by the standard concentration. But in general chemistry, we kind of not worry about that at all. Just know that this is unitless. If you want, let me know. I can make a video on that. Where are we? Okay, so 0 points. So we're just putting in the pressures of the reactants. So 0.35 squared and 0.44. Okay, so we'll plug that into our calculator. 150, 50 squared times 150 squared. Oh, I could have done this a little bit quicker. That's okay. Divided by brackets, 0.35 squared times 0.44. Does that look good? I really like these calculators where you can see what you type. Holy wow, another huge number. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.4 times 10 to the 9. Okay, so 9.4 times 10 to the 9. I think we know which way this is shifting. Oh, maybe not. This is a huge equilibrium constant. Wow. Okay, so just like before, we're going to set up Q and we're going to set up K, and Q is on the left, and Q is 9.4 times 10 to the 9. K is 1.9 times 10 to the 19, which is huge. And which is the bigger number? Well, this is the bigger number, because this is where the Pac-Man's going to go eating. This is the bigger number, so the reaction has to shift to the right here. So reaction shifts right. All right, here's our last one here, and this one's a little tricky for some students, and I hope this one doesn't screw you up. I hope you get this one 100% on it. Oh, shoot. This one's a little tricky, and I hope you don't screw it up. I hope you get 100% on it and that your prof doesn't trick you. Sometimes they try and trick you with a question like this, but I'm going to show you the secret to it. So here we are. So we have this equilibrium system, and we have an equilibrium constant for concentrations. Kc equals 9.8 times 10 to the negative 3 at 550 degrees Celsius. Notice this is for concentrations, and these are gases. We can still determine the concentration of a gas. It's literally moles over liters for molarity. So that's okay here. Now we have 0.500 moles of each reagent are placed in a 2.0 liters flask. Which way will the reaction shift? Now pause the video, see if you can do it on your own, unpause it, and then see if you got it right. So if you're unpaused, this is what a lot of students may do, or some students I should say. So we set up Q, and Q is products over reactants, And we see that there's, so this is concentrations, right? Concentrations of each of them. So concentration of this, concentration of this, concentration of this, concentration of this, blah, blah, blah. So what a lot of students will do is they see the moles of each one and they see the flask and they right away calculate the molarity like this, moles over 2.0 liters for each reagent. 0.500 moles over 2.0 liters, and this is these are the products, and do the same thing for the reactants, and that's fine. You calculated the molarity, but it's not totally correct because your prof is trying to trick you by including solids and maybe even pure liquids in it. You got this part, but you're distracted with these numbers and you kind of forget about this. Some students anyways. So it's tricky the way profs try and kind of throw you for a loop by putting in 3 different concepts. So we're not going to do that. We're just going to kind of go through normal. So we do products over reactants. We'll, rather than plugging in numbers, we'll just plug in what it is for the reaction, one step at a time. So H2O, concentration of H2O, we don't include cobalt solid because it's a solid. And all we have is H2 gas down here. Okay, so that's good. Now the concentration is moles over liters. Right? Concentration is moles, well, not moles over, yeah, moles over liters, moles over volume. And it's 0.500 moles over 1, not 1 liter, whoops, 2 liters. I should include sig figs, 2.0 liters. And that's the same thing in the denominator. You can probably see what this number might be, 0.500 moles over 2.0 liters. Okay, and this is literally the same number in the numerator as it is in the denominator, so it cancels out, and it's equal to 1. And there we are. So we're good. So we will put in Q, we will put in K, and Q is 1, K is a very small, well, not too small, 9.8 times 10 to the negative 3, 9.8 times 10 to the negative 3. It's smaller than Q, so the Pac-Man will face to the left, so the reaction shifts left. And very importantly, just before you go, I think you're good at this, practice, but before you go, it's important to mention that these concentrations will change, the pressures or the concentrations will change, but the equilibrium will not change. So the equilibrium is always going to remain the same. The equilibrium only changes when you change the temperature or the solvent, but the temperature. You change the temperature, you change the equilibrium constant. We're not changing anything when we change the concentrations or the pressures, except for kind of Q. Q is our ratio of products to reactants. That's going to change so that the system reestablishes equilibrium. So K is reestablished. So we're at 1 right now. Initially, our ratio is 1, but the system's going to shift so that the ratio is at 9.8 times 10 to the negative 3. Sometimes on your exam questions will say, which way will the equilibrium shift? And that's not totally right. The equilibrium doesn't shift. Initially, we're not in equilibrium, so it's the reaction will shift so that we establish equilibrium or reestablish equilibrium. Anyways, hope you enjoyed it. Thanks again. I have another video. The next one after this is on ice tables. We'll know which way the reaction will shift and determine what those equilibrium concentrations are at equilibrium. Thanks again. Thanks for watching, and I'll see you in the next video. Cheers.